Yes, sir.
So basically, like in the VLSI, so VLSI is nothing but very large scale integration. So like you know that very large scale integration you have like SSI, okay, SSI, MSI, okay, medium scale integration, large scale integration, and very large scale integration, and ULSI, ultra large scale integration, giant large scale integration. So that means here means some hundred VLSI is nothing but some 100 crores of transistors you are fabricating within an IC. Okay, so like think that some 100 millions of transistors you are fabricating within an IC. Okay, so like you can say that VLSI, if you take example like in previous nowadays you are getting the smart TVs or LED TVs. Those are nothing but those are operating at 16, 12 volts only. Okay, it is taking low power. Okay, so that means here that means it consists of so many ICs. It will do some different operations. It will different functionality. It will do. Okay, so normally compared to like last 10 years or 15 years back, you have like LED TVs. Okay, LED TVs are there. If you see the LED TVs, it will take huge amount of power. Okay, it will take 230 volts or like 50 hertz, and so much of power it is taking. Nowadays, you are getting the whatever the gadgets you are using, that it is taking low power. Okay, so mostly like if you take the VLSI target devices, so mostly we are talking about. What we call so in the VLSI we are talking about one is ASIC, okay. Next one is FPGA, ASIC and FPGA. ASIC is nothing but application specific integrated circuits. Okay, application specific integrated circuit means this IC you are making for only specific application. That is nothing but ASIC. Suppose if you consider some your LED TV or smart TV is there, so that will do only particular application. Okay, so suppose your automatic washing machine is there, you can't change these ICs and you can't use in your automatic washing machines. Okay, so like that is nothing but ASIC. It is only used for specific application. So many applications are there, like if you take the automobiles. Okay, automobiles you have like if you have a high-end car, so you have auto lock braking system and engine control, brake control, airbags. Okay, so inside so many ASICs will be there, and that will be do a particular task only. Okay, that particular task. Okay, and coming to this the example of that ASIC, suppose like you have suppose 3G mobile is there. Okay, 3G mobile. This is support only 3G. So nowadays you got 4G and 5G also you got. Okay. Suppose so what the telecom providers did. So almost most of the people are using 5G. So they decrease the speed of 3G, and they allocated the speed to this 5G. Okay. So what happens? One person he is using 3G. So what happens? He will come to the shopkeeper that I'm not getting that much speed. Okay, what shopkeeper will tell? He will tell that you need to use the 5G. That's why because whoever the mobile providers are network providers are there, they made the speed of this 5G. Okay, you can't convert this 3G mobile into 5G. Why? Because this is nothing but one ASIC. Okay, so these 3G mobile is made with only, it will support only 3G only. Okay, we can't upgrade your 3G mobile into 5G mobile. And coming to the AC also, like suppose if you consider AC, now olden ACs, those are operated with normal remote control only. But now so many ACs are came like so I think Lloyd, I think so. That means you can, there is an app, you can control your AC. You are there in the outside also. Okay, that is nothing but IoT, Internet of Things. Okay, so many applications are there, and you got the electrical vehicles. Okay, suppose like ether vehicle is there. So electrical vehicle, that other vehicle have you have some application. So in that application you can you can monitor where your bike is there, how much charging is there, and what is the condition of that bike. Okay, so olden bikes you can't see that specification. Okay, so that means ASIC is nothing but only used for specific application. Okay, ASIC is nothing but only used for specific application. That is nothing but ASIC. Okay, FPGA is nothing but field programmable gate array. This is nothing but field programmable gate array. So FPGA, where you are using FPGA means it consists of some lookup tables, and it consists of some what we call it consists of some interconnects, and it consists of CLBs, configurable logic blocks. Okay, so we already seen this in the digital. We already seen PLA, PAL, and PROM. We already seen, no? So that means
Yes.
above this, this is CPLDs. CPLDs means complex programmable logic devices. And next you will get FPGA. CPLDs are made with some EEPROM. Okay, EEPROM. Okay, whatever the program is there, that will be there in the CPLDs. But FPGA, it consists of SRAM only. Okay, where you are using FPGA means, suppose like you have a what we call, you have a tower. Okay, you have a tower. Okay, so cell tower, take cell tower. So previously you came with 2G, 3G, 4G, and 5G. Okay, so that means every time the technology is changing in the communication. Suppose in future you will get 6G also. Okay, suppose 6G is coming means you can't that means every time there is a setup in this cell tower, every time you can't change this one. Okay, you can't, this is very costly, and you can't change this one. So here you are using FPGA. Okay, every time the technology is changing means you will reprogram your FPGA based on your requirement. Okay, that is FPGA. And in defense also you are using defense, airways, or navy. Okay, we are using. So in defense, so many so many weapons are there, no? So many weapons and drones are there. Okay, every time the technology is changing means that weapons are very costly. Okay, so we can't buy again and again. So there we will deploy this FPGA. So if technology is changing means based on our technology requirement, we'll program this FPGA. Okay, so that is the mainly we are talking about this VLSI and ASIC. And also we are talking about this SoC, system on chip. SoC is nothing but system on chip. Okay, all the peripherals whatever the ARM processors and whatever the peripherals are there, those are there in the SoC, system on chip. Okay, and IPs also we are talking about. IP is nothing but intellectual property. Okay, IP is nothing but intellectual property. Suppose you have single port RAM, dual port RAM, and some FIFO, and some I2C, SPI. These protocols are nothing but we call as IP, intellectual property. Okay, now you coming to the ASIC design flow. So ASIC design flow, if you see, suppose design specification. Design specification means, so first any IC is there. First designers will decide that IC is used for which application. Okay, let us take that IC is used for networking purpose, or IC is used for what we call communication purpose, or IC is used for some other defense purpose. Okay, first you need to find out the application of that IC. Okay, after that, in the design specification, we will do about the power related, how much power it will take, how much area it will take, and how many inputs are there, how many outputs are there. All those things are taken by the design specification. Okay, design specification means suppose if you take any device. Okay, first device, the company people will give the data sheet. So based on the data sheet only, if you purchase any equipment also, they will give the data sheet. Data sheet, all the information will be there. Okay, so it's like a specification. How much time, how much area it will take, how many inputs are there, how many outputs are there. So these are nothing but design specification. So there are architectural engineers. Architectural engineers. These engineers are highly experienced persons, mainly 25 to 30 years experience. They will take the design specification and they will do the architecture. Okay, architecture is nothing but what you already studied about computer architecture. So in the computer architecture, what will be there? So what are the components in the architecture, and how the algorithms are there, how the software is there, all about that computer you studied in the architecture. So like that, suppose if you design any CPU, okay, CPU. So in CPU, what will be there? In CPU, what will be there? ALU is there, memory unit is there, and control unit is there, bus interface unit is there. All those things are there, no? So how we are doing the architecture? How we are planning means how we are doing the architecture. So where the block should be placed, IO block should be there placed, where the um, uh, this macro level blocks which should be placed. Based on that, you will do the architecture. Okay. Micro architecture means basically like the sub modules are there, no? Submodule architecture is nothing but micro architecture. You need to design an ALU. You need to design again memory. You have RAM, ROM. Okay, these you will design by using micro memory unit and control unit and bus interface unit. All those things are nothing but micro architecture. Okay, first architecture. So that chip is used for, suppose if you want to design SOC. In SOC, what are the peripherals are required? You need to use ARM processor. You need to use some peripherals like I2C, SPI, UART. Okay, all those that should be connected with AMBA protocols. That means that should be connected with AHB. Okay, AXI bus interface. So those are, so all those architecture is done by the architecture or micro architecture. And next RTL design. Okay, RTL will discuss. RTL is nothing but register transfer level. Register transfer level. So register transfer level means, so basically like there are two languages are there. Okay. So first of all, I will tell you the difference between software language and hardware descriptive language. Software language means the software people. So you know the software language. What are the software language? C, C++, Java, Python. Okay, these are the software languages. So these software languages, they will make the application only. Suppose for the banking system, they will make the application and they will give it to the banks, and based on that bank application, that workers will work. Okay, railway ticketing system, they will make the application based on the, they will do the some programming and they'll make the application and they'll give it to them. Okay, they will only do the application only, but HDL is nothing but we can make the hardware. By using HDL, we can make the hardware. So there are two types of HDL are there. Hardware descriptive language. Hardware descriptive language is nothing but, we already studied the digital combinational circuits, sequential circuits. In combinational circuits, what will be there, and in sequential circuits, what will be there, and we already seen the FSMs. Okay, so like we are describing the operation of this these digital circuits in textual format is nothing but HDL. Okay, so we are describing the hardware, describing the operation in terms of textual format. In terms of programming is nothing but HDL. Okay, so HDL, there are two types are there. One is Verilog and next one is VHDL. Verilog and VHDL. So Verilog is nothing but this will follow C syntax, and this will follow olden languages like Ada and Pascal. Okay, and it is hard syntax is there, and hard to learn. And VHDL is nothing but very high speed integrated circuit hardware descriptive language. Okay, and Verilog is nothing but Verilog HDL only. Okay, this VHDL we are using in defense, I think, so defense. Okay. Um, I think during in your BTech you studied Verilog or VHDL. I'm expecting response from you. Hello.
Verilog, sir.
Verilog. Yeah, Verilog. Yeah, Verilog is easy syntax and easy to learn. And if you know the C, so it is easy to easy to write the program in Verilog. Okay. So Verilog is globally you can access. Okay. So corporate or whoever the corporate things are there, and they will use a Verilog only. If you go to US or any other countries for the RTL design, they are using Verilog only. They are not using VHDL. VHDL they are using for defense purpose only. Okay, so like this. Okay, so in Verilog there are some different types of modeling styles are there. One is switch level modeling, and next gate level modeling, and data flow modeling, and next you have behavioral modeling. Okay, so here switch level modeling means for basic low level modeling like CMOS inverter you are writing, that is switch level modeling. Gate level modeling means you need to write in terms of gates. Okay, you have gate level primitives are there, you are writing in terms of gate level modeling. Okay, data flow means in terms of expressions you need to write. Suppose like AND gate is there. You write in terms of expression y equal to a and b. Okay, you need to use assign statement. Okay, that we'll discuss. Don't worry. And behavioral modeling means you know the behavior of the circuit only. So AND gate means I know the behavior. What is the behavior? If any one of the input is low, the output is low. Okay, I know the behavior only. So here I will write. I will use some procedural blocks like initial or begin, and I will use some procedural statements like if, case, else, while, okay, for loop, all those things we are using. Okay, whatever we are using in the C, we are using in the behavioral load. So these two models, we write the program in RTL. So RTL design, we do the synthesis. Synthesis is nothing but we are converting our program into hardware. That is nothing but gate level netlist. Gate level netlist. Okay, so normally gate level netlist means internally what happens means it is converted into registers. Okay, flops. It is converted into flops. Flops is nothing but D flip flops. Okay, so how the data is transmitting from one flop to other flop is nothing but RTL. RTL is nothing but register transfer level. Register transfer level. So here basically we are using Verilog. Verilog. Okay, so Verilog. For this you need RTL engineers, we need RTL engineers. Okay, and Verilog, we can write the Verilog code, and for verification purpose you can write the test bench. So up to FSM we can write the test bench. Okay, so that means this is a designing language. We can do verification also, but the verification is static in nature, and in the black box we are verifying. Okay, we are not that much doing. So 30% only will do verification. Okay, if you want to do verification, so verification is nothing but correctness of your design, whether your design is correct or not. That is nothing but verification. Okay, so for that verification you need RTL verification. RTL verification is nothing but mm, in this you use system verilog and UVM. System Verilog and UVM. SV is nothing but this is also used. This is one HTL. Mainly some main character properties are there compared to Verilog. Okay, so we have like polymorphism, randomization, constraint randomization, and I think you studied about OOPS concept. I think in C++ you studied about OOPS concept. OOPS concept comes in SV. Okay, you have child class, a parent class. Okay, and there is a handle, and all those things will come in the SV. Okay, and this is also HDL. So by using SV, we can verify that circuit. And UVM, like UVM is not a language; it's a methodology. It's a methodology. Okay, so like SV, there is no particular test bench is there. Suppose if you want to write test bench for I to C, separately you need to write. Suppose if you want to write for test bench for UART, separately you need to write. Okay, that is a robust test bench. Okay, so what this company people has decided, we want a unique verification methodology. We need a unique test bench. That is nothing but they came with this UVM, Universal Verification Methodology. Okay, this is a methodology. Okay, this will use SV. Okay, this will use SV, and it consists of some UVM factories, and in that factories, then standard libraries are there. So like they will write the test bench with some like environment driver class. So many classes are there. Okay, So many classes are there. They are writing in this for the program for UVM. Okay. So for this you need DV engineers, design verification engineers. Okay, DV engineers are required. Okay, DV engineers design. So ASIC DV also we can call ASIC DV. Okay. So these both will work together. These RTL engineers will design by using Verilog, and these verification engineers will verify this design is correct or not. Okay, design is correct or not. Okay, if design is met, it will go to the next state. If design is not met, it will go to the RTL design. Okay, and after that, logic synthesis. What is this logic synthesis? Logic synthesis is nothing but normally here after verification, you will get a gate level netlist. You will get a hardware gate level netlist. Okay, gate level netlist. This is uh, not optimized. This is not optimized. Okay, so in order to do with optimized, so this synthesis engineers are there. Okay, who are the synthesis engineers? Okay, so this synthesis engineers, what they will do, synthesis engineers, these engineers will work under constraints. Those are nothing but ATP, area, time, and power. Area, time, and power. Okay, these are the constraints we call as constraint. Okay, so for the VLSI, so area should be less, and timing should be like it should be as fast as possible. So timing should be less. Power, it should take low power. Okay, why? Because most of the now we are using handheld devices. Those are battery operated, so that will take less power. Okay, so ATP is nothing but they will work under this ATP. ATP is nothing but area, time, and power. And next you have DFT engineers. What are these DFT engineers will do? DFT engineers, they will give some scan. Means this is like testing. Okay. DFT is nothing but like a testing only. So like there is some scan chain, BIST, built-in self-test. Okay. They will give some test vectors to your design so that your design is working, means meeting the specifications or not. Okay, your design is meeting the specifications or not, they will check. So for this you need a DFT engineers. Okay, and logic equivalency check. Logic equivalency check means what? Logically they will check that your design is meeting this specifications or not. Okay, design is meeting this specifications or not. Okay, and next STA. Okay. So during this verification, you can simulate also. You can simulate with the waveforms, whether your design is correct or not. They will simulate. And here also, one more sixth one I'm writing. There is a formal verification. Formal verification. Formal verification means design verification means you need to design by using this language, that is SV and UVM. Okay. Formal verification means you need to apply some mathematical formulas. Okay. Such a way that your design is verifying. Okay. This specification. Okay. By using those are nothing but we call as FE engineers. Okay. Formal verification engineers. Okay. And next. Preload STA. The STA is nothing but static timing analysis. Static timing analysis. Okay. Static timing analysis means in the digital, we already seen that one AND gate is there. Okay. One AND gate, you have A and B, and output Y equal to what? A and B. So you are getting the output at a 0 time units. 0 seconds, 0 nanoseconds are time units. You are getting the output. But there will be some propagation delay for this gate. Okay, there will be some propagation delay for this gate. Okay, so in the STA you are learning about propagation delay, setup time, and hold time, and violations. Okay, if setup time and hold time is not occurring, what are these violations? And clock skew and clock jitter. Okay, clock jitter, all those things you will learn about this pre-layout STA. Okay, and next this pre-layout STA, and it is there in post-layout STA. Post-layout STA. Okay, And if design is met, it will go to the next, and design is not met, it will go to the initial state. Okay, and next there is a PD flow. Okay, for this you need a STA engineers, STA engineers, separate STA engineers will be there. Static timing analysis engineers are there. Okay, and next PD flow. So PD flow means suppose if you take the PD flow, so in the PD flow you have partitioning, floor planning, power planning, placement, clock tree synthesis, routing, timing closure, all these things are there. Okay. Suppose PD flow means you are taking the input from this your front end, and you will make an IC. Okay. Suppose I will tell you with one example. Suppose if you are building you are constructing, civil engineer is there, constructing any building. First, what he will do? He will do planning, no? How the building should look like. He will draw the planning. Okay, that is nothing but where the uh, so planning and partitioning also will do where the bedroom should come, where the hall should come, and where the kitchen should come. Okay, like that. Okay, they will do this and placement of macros. Clock tree synthesis is nothing but you have a global clock and all modules will not work at same clock. No, so clock tree distribution. Okay, routing is nothing but connections. You are doing the connections and timing closure, all those things will be done by the PD engineers. Okay, I think you are doing PD course. That PD engineers will be done. Okay, so this is you have PD engineers. Okay, you have PD engineers. For this, you need a PD engineers. Okay, and the parasitic extraction is nothing but uh, so inside you are fabricating means with copper wires. So copper wires have some R and C, resistance and capacitance is there. Okay, removing of this resistance and capacitance is nothing but parasitic extraction. Okay, and you have post layout STA. Okay, and if design is met and it will go to the next step. If design is not met, again it will go to the PD flow. Okay, so here you have PV. PV is you also PV engineers are there. PV engineers. PV engineers means nothing but physical verification engineers. Okay, they will do some verification. Verification will be done in the front end as well as verification is done in the back end also. Okay, after physical verification, there is a GDS2 file. GDS2 file will be generated. Okay, a graphic design system, some GDS2 file will be there, and that is given to fabrication. So in the fabrication, by using NWEL twin tube technique, you will fabricate your IC. Okay, so many things are there. You need to study about this fabrication, about diffusion and implantation, photolithography, and etching. Okay, and all those things. So we need to we need to grow a pure silicon through Zokrasky method, that is CZ method. Okay, all those things are there in the fabrication. Okay, as a PD engineer, you need to know about this fab also. Okay, so this is about ASIC design flow. Did you understood any doubts or any queries in this? So total, how many engineers are required? Total, you need 10 to 15 VLS engineers are required. VLS engineers are required. One person will not do all these things, no? So different thing and different engineers are there. Okay, different department is there, and you have service-based companies that will do some things, product-based companies that will give that will produce the products like that, and EDA companies are also there, like Cadence, Synopsys, Innovas, they will produce the tools, all those things. Is it fine? Shall I move forward?
Yes, sir.
Okay. Any doubts or any queries? Yeah. Why this VLSI, this ASIC design flow? Why it is going into all these steps? Can anyone say? Can anyone unmute yourself and say?
So to reduce the failure of chip.
Yeah, to reduce the failure of step. Okay, correct only. So that means here, like So rigorous verification and designing process is taking out, and rigorous testing is taking out. Okay, rigorous design is taking out. Why? Because here, suppose you made one IC, okay, one chip, okay. So one chip you are using for what? A real-time application. No? So real-time application means suppose if you are using for any railway related or in the railways, okay, in the train or in any airplane like. So let us take one example like aeroplane you are using. Okay, that IC you are using in the aeroplane. Suppose any failure in that IC, okay, can damage not only the property, it can damage the lives also. Okay, it will damage the lives also. Okay, so before coming into this market, okay, coming into the market, I think to make this ASIC, it will take around 1 year. 1 year. Okay, it will take low power consumption, and mainly used for specific application. Okay, so this is the main like ASIC design flow. Okay, yeah. Shall I move forward?
Excuse me, sir.
Yeah, yeah. Tell me.
So you mentioned about formal verification, no? Is it done in pre-layout or LEC?
In front end they will do.
Okay, in
Here,
front end.
here in the verification, RTL verification is there, no? RTL
Huh.
verification. This is nothing but we call as design verification. This is nothing but what? Design verification. Design verification means you are using UVM methodologies to verify that correctness of the circuit. Okay. So
Yes.
why we are using design verification means up to FSMs you can verify with Verilog. Okay, you can write the code and test bench. Suppose like complex IPs are there, complex SOCs are there. Suppose like complex IPs means you have ISM processor or Ryzen 7 processors and system on chip, suppose Raspberry Pi, and so many complex IPs are there. So that IPs with the Verilog we can't verify. So we need to go for this UVM related methodologies. Parallelly with the mathematical formulas, you need to verify that this is matching your specification. That is nothing but formal verification. That
Okay.
will be come in the
Okay,
front
sir.
end only, not back end. Okay. So front end
Okay, sir.
means up to synthesis we can call as front end. Up to synthesis we can call as front end. Okay. So here you see. So that means up to circuit design. Okay. This is nothing but front end. Okay. Remaining DFT, these STA and all those things, PD, this will come in the back end only. Understood?
Yes, sir.
Okay. So here you see, so these are the physical design, floor planning. Okay, how so this you are going to study. Okay, just I'm not going deep into this. Floor planning. That means planning your floor being die. Okay, die means what? It's like a what we call. It's like a CD only, like a papad only, like that thin layer of die will be there. In that you can fabricate so many processors in that. Okay, die size estimation, IO macro placements, and all those things you'll study about physical design. Okay, floor planning, how the macros will be placed, how the RAM will be placed. Okay, this you will do in the tool itself. Okay, like that you will study. And what are the inputs for PD means I told you, no. So these are the inputs. Okay, you are going to study like .v file. .v file means netlist. I told you synthesis, no. What is the synthesis? This EDA tools means in the front end. In the front end, you have some EDA tools like Synopsys tools, Synopsys, Cadence tools, and AMD Xilinx Vivado, and some Cadence you have for verification you have Jasper tool, and for verification you have Costa Sim, and for Verilog you have Model Sim. Okay, all these tools, Quartus Prime, these are nothing but tools. So tools, what they will do means they will convert, they will synthesize and they will convert your code into gate level netlist hardware. Gate level netlist is nothing but hardware. Okay, so why you are using EDA tools means I told you like you are working under some millions. some 10 100 millions of transistors which is fabricating within an IC. Manually it's not possible, with tools only it's possible. So we are the VLSI engineers, we are giving guidelines to the tool such a way that tool will work. Okay, so the input for PD is .v file, that is gate level netlist. Okay, I told you the constraints, no constraints. What are the constraints? ATP, area, time, and power. These are the constraints. Okay, these are coming from the synthesis people, and some logical library files, and physical files, .lef files, and multi-voltage domain design files, UDF files. Okay, this PD people, you are the PD people, will take the input from the front end. Okay, these are the inputs coming from the front end, and you'll do all those things. Okay, what will you? We'll do the floor planning. Okay, estimate the die size and minimize the core area. Okay, planning for the cores, where the macros should be placed, where the IO should be there, and IO planning and power planning. All those things you will do in the floor planning. IO planning also you'll do. Like suppose if you receive three different types of input from FE regarding IO ports, how to design this IO ports? That is IO planning. Okay, and core area. Core area means a standard cells, as I told you, no. During VLSI technology, I told you standard cells are available in terms of NAND gate, NOR gate, and D flip flop, or it is available in full adder circuit. Okay, those are nothing but standard. Already standard cells you can, how you can place in the floor planning elements. Like that, you will study about this floor planning elements placements. It will show the exact location of core area and standard cell placement, and how we should place this soft modules. Okay, just I'm not aware of this. Just I'm giving the idea about your how you are going to study about these placements and all those things in the core related. Okay, so actually I'm I'm specialized in front end only, but just I'm giving the idea about this. Okay. So clock tree synthesis, you have a global clock, and each module will not operate the same clock, no? So that means how the clock is dividing. You need to know about timing, power, area, and signal integrity. Routing is nothing but like connections. Okay. So you will study about global or track routes. Okay, connection, how the connections are made between the signals and metal layers. Okay, local connectivity and physical connectivity, and how to fix the DRC. DRC is nothing but design rule checks. All those things you are going to study in the routing. Okay, and sign off checks or physical verification means I told you, PV engineers. Okay, so after making all those designs, floor planning, placement, routing, and all those things, you are going to study about sign-off checks like electrical, physical verification, and crosstalks. In electricals, you are going to check power estimation, IR drop, power EM, signal EM, and in physical verification, you are going to study about layout versus schematic. Whether your layout is matching your schematic or not. Okay, that is LVS. Okay, design rule checks. Design rule checks means some area width that is matching or not. Those are nothing but design rule checks, antenna checks also, and crosstalks. Okay, all those things you are going to study in the sign-off checks. Okay, is this fine? Any doubts or any queries in this? Just I'm giving idea about this physical design flow and all those things. Hello.
Yes, sir.
Okay. Suppose if it is FPGA means, I'll open this FPGA. One second. I'll give some overview of this FPGA. Yeah, this is the basic design flow of FPGA. Okay. So, like design flow means design specification, behavioral description. So I need to have the behavior of the circuit. What is the behavior of the circuit? RTL design. Here also we'll write the program with RTL design, VHDL or Verilog. Okay, I told you, what is the difference between high level language, that is software language, and HTLs. These are concurrent. Concurrently, we can execute. Parallelly, we can execute. Whereas software language will be executed sequentially. Okay. And functional verification and testing, logic synthesis. We need to do logic synthesis. Technology netlist means what? You need to do some floor planning, placement, and routing, and all those things will be done in the technology netlist. Okay. And what type of board you are using? You have some different types of FPGAs are there, like Altera, Xilinx, and some so many companies are there. Those you need to map, that is technology mapping, place and route. After place and route, you'll generate the bit stream. Bit stream is nothing but this is like one type of X file only. Okay, X file, like I told you, like our electronic ICs that will understand only zeros and ones. Okay, in the embedded also, in the microprocessor and microcontroller also, you done some experiments related to microcontroller and microprocessor interfacing with this external peripheral like LCD, LED, seven-segment display, or stepper motor. There, what you are writing? You are writing the Verilog sorry, you are writing in assembly language. That assembly language program you are converting into X file. That X file you are loading into your board, so that your board is working according to your application. So that is nothing but bit stream generation in terms of X files only, in terms of zeros and ones only, and that you are programming into this FPGA downloading. Okay, this is basic FPGA design flow. Okay, and coming to the architecture of FPGA. So this is the architecture of FPGA. So basically it consists of like IO pads, okay, and these are the interconnects, and these are the switch blocks, and this is nothing but a logic block, okay. So why these IO blocks are connected all sides means, suppose let us take here, this is my FPGA, only here IO blocks are there, okay. So if you connect the input directly, you can connect. Suppose if you connect output from here, you need to connect. From here you need to connect now. So that's why IO blocks are connected all sides. Suppose here, from here you need to connect input, and here you can connect output. Like this you can connect the input and output, all those things. Okay. And so FPGA, the heart of the FPGA is nothing but this logic block, or we can call as CLB, configurable logic block. Okay, this is nothing but CLB, configurable logic block. So configurable logic block consists of what? A lookup table. This is nothing but lookup table, okay, and D flip flop, okay, and it consists of mux, okay, and so that means here lookup table means, suppose if you want an AND gate, if you want an AND gate, what you will do? You will write the Verilog code or a VHDL code, and you will generate the bit stream, and you are load into this FPGA. So in this lookup table, the AND gate will form. AND gate like structure will form. Okay, so like this, the output of the lookup table is given directly through one input as mux, and other input through the delay. Through the delay you are giving the input. Okay, through the D flip flop. D flip flop we already studied, no, like delay flip flop. So through the delay, you are giving the one of the input to the mux, and you are getting the output. Okay, so this is the heart of this any FPGA, configurable logic block, CLBs. Okay, so CLBs consist of how many inputs? Four inputs and one output. Okay, four inputs and one output. So like this, how many CLBs are there? Nine CLBs are there. So nine fours are 36 inputs you can accommodate, and nine outputs. 36 inputs and nine outputs we can accommodate. Okay, nine outputs we can accommodate. Okay, and coming to this one, which one? This interconnects are there, no? So interconnects are connected with the switch matrix. This is nothing but switch matrix. Okay, so this is each switch matrix point to six routing switches. Okay, so these interconnects are connected with this switch matrix. So how the switch matrix will be there means, four transistors are there. So no, sorry, six transistors are there. Six fast transistors is there. Fast transistors are connected like this. Suppose here you want to connect from north to west. This transistor should be on. Okay. If you want to connect like this, these two transistors should be on. And if you want to connect like this, these two transistors should be on. And if you connect from west to east, this transistor should be on. Okay, like this, it consists of so six pass transistors. Okay, pass NMOS transistors. It consists of NMOS transistors. Okay, and so like this, it will connect. Okay, like this, it will be connected to the main. So basically, this consists of SRAM. Okay, SRAM. It consists of what? SRAM. So SRAM means what I told you. SRAM is a volatile. How the switching is happening means how the programming is happening is through the SRAM cells. So as this is volatile, as the power is gone, whole programming will be arranged. Okay, in the FPGA. Okay. So basically, what is the technology you are using? Three types of technology you are using. SRAM technology, that is static random access memory. I think SRAM we already studied, no? SRAM is a 60 RAM cell. We already seen. It consists of latches and two pass transistors and one more antifuse technology and EEPROM and EEPROM technology. These are the technology we are using in the FPGA. Okay. So SRAM technology means like this we already seen. Okay. One pass transistor, one latch is there. So that if you want to store one bit value, word line and bit line. Okay. Word line should be one and bit line should be one so that it will store one value. Okay, and we can read or write the data into this SRAM. Okay, so this is 60 SRAM cell we already seen. Okay, anti-fuse technology means what? Initially, this is not in a fused condition. So this is in fused condition. We need to make this as unfuse by programming. Okay, that is unfuse anti-fuse technology. So there are two metals are there. So normally it is in fuse technique. So that by applying some voltages we can anti-fuse. So that we can make anti-fuse. Fusing is nothing but in the whole household. We already seen that means that is connected with one wire. That is nothing but fusing. Anti-fuse means what? Already it is there in fuse technique. We need to make anti-fuse. We need to program by using. We need to separate these two metals. That is nothing but anti-fuse. Okay. So that is anti-fuse technology. Okay. And EEPROM means this is volatile. By using EEPROM or EEPROM, erasable programmable read-only or electrically erasable programmable read-only memory, will erase this. Okay. FPGA families, if you see, there are like Altera, Flex, Spartan, Vertex, Artix. Okay, all these are there. So these Altera, Flex, and Spartan are low power families. Okay, and Vertex is high power families. Okay, and these are moderate families. So these are used for laboratory purpose only, for education purpose, and this is used for industry level. Vertex is used for industry level. Okay, Spartan is from Xilinx, some Xilinx XC4000, XC5000. These are the families. Okay, these are the old families. Okay, so Altera family. This is the basic architecture of Altera family. Okay, and next Xilinx family. It consists of CLBs. See here, it consists of CLBs, switch matrix, and IO buffers. All this it will be there. Okay, this is XC4000 CLB. Okay, so all these things. Xilinx Spartan. Okay, this is the architecture of Xilinx Spartan FPGA. Okay, so like this, you have Vertex FPGA. Okay, all those things are there. Okay, this is about FPGA. So we covered. One second.